Okay, in this video we're going to look at the notion of a balancing number. So the definition goes like this. We say n, which is a natural number, is called a balancing number with a balancer of r if the sum 1 plus 2 plus 3 all the way up to n minus 1 is equal to the sum n plus 1, n plus 2 all the way to n plus r. So you can think that like r balances the numbers before n and a certain number of numbers after n when you sum them. So I like to think about it with this picture. So we've got this scale. N is like in the middle of the scale, so it's like the point of the teeter-totter. And then we have this sum 1 plus 2 all the way up to n minus 1 has the same weight. In other words, it has the same sum as the sum n plus 1 up to n plus r. Okay, so now that we have this picture, let's look at some of the first examples of balancing numbers. So the first example is 1. So I mean, this is kind of a trivial example, but it's generally agreed upon that we include 1 as a balancing number, and here the balancer is like the number 0. So notice we have the sum of everything smaller than 1, well that's just 0, and the sum of 0 numbers bigger than 1, so obviously we have 0 equals 0. So here, if we're keeping a list here of balancing numbers, then the first one would be the number 1. And actually some people include 0 as the first one, but we'll not do that. We'll include 1 as the first one to go with our definition that it has to be a natural number. Okay, so the next example would be 6. And that's because if we take 1 plus 2 plus 3 plus 4 plus 5, notice that's equal to 15. But now 15 is the same thing as 7 plus 8. That's also 15. So we have the sum 1 to 5 is the same thing as the sum of 7 and 8. So in this case, our r, so our balancer, is the number 2. Because we need 2 numbers past 6 in order to equal the sum of all of the natural numbers before 6. So that makes 6 our next balancing number. Okay, so the next one after 6 is 35, and that's because 1 plus 2 plus 3 all the way up to 34, so you can easily check that that's equal to 595, and then you can also check that if you take 36 all the way up to 49, that is also equal to 595. And you might say, well, what's the balancer in this case? Well, you can check that the balancer in this case is the number 13. And that's because we take 13 numbers over there on the right-hand side. Okay, good. So that makes 35 the next balancing number. Okay, so now what about the one after that? So the one after that is 204, and you can check that if you take 1 plus 2 all the way up to 203, if you add all of those numbers together, you'll get 20,706. Okay, good. And then if you similarly take the sum 205 all the way up to 288, then you'll also get 20,706. And in this case, you can check that your balancer is equal to the number 84. So we've got a new balancing number 204, and the balancer is 84. And so let's see, we can add that to our list, 204 as the next balancing number. Okay, so now instead of like going on looking at examples of these balancing numbers, what I'll do is I'll clean up the board and we'll work towards describing them in general. Okay, so let's recall that we say n is a balancing number if the sum of the n minus 1 natural numbers smaller than n is the same thing as the sum of the r natural numbers larger than n. And here r is equal to the balancer. So let's go ahead and simplify this equation a little bit. So notice that the left-hand side is a triangular number, and it's well known that those have a closed form. And in fact, we can take 1 plus 2 plus 3 all the way up to n minus 1, we can add that together and we'll get n times n minus 1 over 2. So there's a bunch of videos on YouTube where you can check that this is the closed form for a triangular number. Okay, good. Now let's go ahead and look at the right-hand side and see if we can simplify that as well. So notice we'll take n plus 1 plus n plus 2 all the way up to n plus r. And notice we can put all of the n's together. So this is equal to n plus n all the way up. And now how many n's are there? There are exactly r n's. And then after that we have 1 plus 2 all the way up to r. Great. But now we can simplify this a little bit. So notice that is going to be n times r. That's actually exactly the definition of multiplication, is repeated addition. And then we have another triangular number here, so we can use the formula for that as well. So that's going to be r times r plus 1 over 2. Okay, good. And actually, since we want to set these equal to each other, it's probably going to be useful to factor a 1/2 out of this to make that a little bit easier. So let's go ahead and do that. If we factor a 1/2 out of this, we can think of this term as having 2 over 2 in front of it. So we're going to get 2 times nr plus r squared plus 1. So we get something like that. So now we have this equation has to be equal to that equation. So we're on track to being able to describe these balancing numbers. Okay, I'll clean up the board and we'll look at that equation in a little more depth. Okay, so I've moved the equation to the top of the board. I've rearranged things a little bit, and I've corrected a small typo that was on the last board. So look for that if you're interested. So we've got 1/2 times n minus 1 is the same thing as 1/2 times r squared plus 2nr plus r. So notice we can get rid of those 1/2s immediately just by multiplying this equation on the both sides by 2. And then that's going to give us the following equation. So we have n squared minus n equals r squared plus 2nr plus r. And now we have two things that we can do. We can maybe like use the quadratic formula to solve this for r, or we can use the quadratic formula in order to solve this for n. And in fact, it's going to be most useful to use the quadratic formula to solve for r. So let's go ahead and write this in a form that we can do that. So we'll have r squared plus, now we can factor an r out of this. That'll leave us with 2n plus 1 times r. And then we're going to have this as plus n minus n squared equals 0 after we move this over to that side of the equation. Now we can use the quadratic formula in order to solve for r. So notice that's going to give us r equals, so we have negative the b term, so that's going to be minus 2n minus 1, and then plus or minus, but I'll just say that we only need to keep the positive result because we're working over the natural numbers, and that r is also a natural number. In other words, it can't be negative, and if we let this be negative, we will only have and the case when we have the negative will only give us negative numbers. So we have plus the square root of, so b squared, so that's going to give us 2n plus 1 squared minus 4 times a times c, so that's going to be minus 4 times n minus n squared. Good. So we've got something like that, and then that's going to be all over 2. Okay, so now let's see if we can simplify this. So that's going to give us minus 2n minus 1 plus the square root of. So notice if we multiply this out, we're going to get 4n squared plus 4n plus 1. So that's what we get there. And then if we distribute this minus 4, we get minus 4n plus 4n squared. So notice the 4 n's cancel, and we're going to get 8n squared plus 1. So we have 8n squared plus 1 all over 2. Great. Now notice here we're taking the square root of an odd number. We also have an odd number there. The square root of an odd number, if it is an integer, will be odd. So that means we'll have an odd number plus an odd number over 2. So this is always an integer. In the special case when 8n squared plus 1 is a perfect square. So we need, like I said, 8n squared plus 1 to be a perfect square. And in fact, every time that 8n plus 1 is a perfect square, that makes r into a natural number, which means we will have a balancing number and a balancer. So let's just reiterate, if 8n squared plus 1 is a perfect square, then n is a balancing number, and r, which is defined by that formula over there, is its balancer. Okay, so I'm going to move that to the top, and then we'll talk about how to figure out what values of n arise from this situation. Okay, so on the last board we got to this point. N is a balancing number if and only if 8n squared plus 1 is a perfect square. In other words, we can write 8n squared plus 1 equals m squared for some natural number m. So let's notice that we had our list of balancing numbers already. And so notice if we have n equals 1, so that makes 8n squared plus 1 equal to 9, which is equal to 3 squared. So we're good to go there. So in other words, the ordered pair m comma n equals 3 comma 1 is a solution to this equation. And I should say the m part of the solution is not super important for our goal of finding balancing numbers, but it is important for finding solutions to this equation. Okay, and so now next, if n is equal to 6, that makes 8n squared plus 1 equal to 289, but that's equal to 17 squared. And so you can check that. So remember, n equals 6 was a balancing number, and that corresponds to a solution to this equation of 17 comma 6, which again, the m value of the solution is not really super important for the balancing numbers, but it is important for solving this equation. Okay, so now the next thing I want to do is move to classify the solutions to this equation. So I'll clean up the board and then we'll get to that. Okay, so along our goal, we're going to look at the following claim. So if xy is a solution to this equation, m squared minus 8n squared equals 1. Now notice that's exactly the same as the equation m squared equals 8n squared plus 1, but this is going to be a more useful form for us. And I should say that this is known as a quadratic Diophantine equation, and equations like this were studied throughout the history of mathematics. In fact, the way that we're going to create new solutions was discovered by Brahmagupta, who was an Indian mathematician. Okay, so if xy is a solution to this equation, then so is xk, yk, so that ordered pair, where we define xk, yk in the following way. So xk plus yk times root 8 is the same thing as x plus y times root 8 raised to the kth power. So sometimes this x and y are called the fundamental solutions, and in general it's kind of hard to find the fundamental solutions for equations like this, but in our case we know them from looking at those balancing numbers earlier. And I should say that we can equivalently define xk and yk by the following equation. So we have xk minus yk root 8 is the same thing as x minus y root 8 raised to the kth power. So good. So we're going to prove this by induction. So notice our base case is pretty easy because that's just k equals 1. And we know that x squared minus 8y squared equals 1, so that is a solution to this equation. Okay, so now we want to make our induction hypothesis, which will be the kth case is true. In other words, we will suppose that xk squared minus 8yk squared equals 1, and consider the following equation. So we want to consider xk plus 1 squared minus 8yk plus 1 squared. And we want to show that that's equal to 1. Okay, so now what we'll do is we'll factor this. So notice we can factor this in the following way. Xk plus 1 plus yk plus 1 times root 8 times xk plus 1 minus yk plus 1 times root 8. Okay, good. But now, notice that by this equation, we can write this in the following way. So we can write this as x plus y root 8 times xk plus yk root 8. So that's what we can do to this first term. Good. And then to the second term, we can do something similar. So this is x minus y root 8. And then this is xk minus yk root 8. Good. And now what we'll do is we'll strategically recombine these. So we'll combine this one with this one. And then we'll also combine this one with this one. And so notice combining the red ones will give us x squared minus 8y squared. So that's what we get from combining the red ones. And then combining the blue ones will give us xk squared minus 8yk squared. Good. And now notice the red thing is equal to 1 by our setup, because we're assuming that xy is a solution to this. And then the blue underline is equal to 1 because of our induction hypothesis. So this is equal to 1 times 1, which is equal to 1. Which means that xk plus 1 comma yk plus 1 is a solution to this equation, which proves the claim. And now something that's part of the claim, which I won't prove, which isn't written here, is that all solutions to this equation are in this list generated by xk and yk. Okay, so I'll clean up the board, we'll state that, and then we're almost to the point where we'll have a formula for these. Okay, so on the previous board we proved that if x and y were solutions to this quadratic Diophantine equation, then xk, yk are also solutions. And something I'm not proving but is a fact is that all solutions to this Diophantine equation are gotten from this formula. Okay, good. So now I want to play around with this formula a little bit to see if we can get a handle on what these numbers xk, yk are. So here's what we'll do. So notice xk plus yk times root 8. So that's going to be equal to x plus y root 8 to the kth power. Great, but notice that that's equal to x plus y root 8 times x plus y root 8 to the k minus 1 power. So that's easy to check. But now notice that that's equal to x plus y root 8 times x sub k minus 1 plus y sub k minus 1 times root 8. Because that's exactly how xk minus 1 and yk minus 1 are defined. So now what we can do is FOIL this out, and notice we'll get x times xk minus 1, and then we'll get plus 8 times yk minus 1. Now I'm going to put those in parentheses. Good. So those are the parts that are not connected to root 8. So I got that from multiplying this term and this term, and this term and this term. So now I'll look at what we get from the other terms. And so notice that's going to give us plus x times yk minus 1 times root 8. Good. And then plus xk minus 1 times y times root 8. So I'll put those in blue. Okay, good. Now what we can do is we can equate the stuff that I have in red on each side of the equation and the stuff that I have in blue on each side of the equation, but not actually everything in blue, just the stuff that is the coefficient of the square root of 8. And this has to do with the fact that since the square root of 8 is an irrational number and everything else is a natural number, there's some sort of separation between these two types of terms. So now notice that's going to give us the following formula. So we'll have xk is equal to x times xk minus 1 plus 8 times yk minus 1. Good. And then we'll have also yk is equal to x times yk minus 1 plus xk minus 1 times y. And so now let's recall that we have a solution, and that solution is xy equals 3, 1. And so we can check that. So 3 squared is 9, minus 8 is 1, so that's a solution. And then notice in this case, the y variable is giving us the balancing number. So that's our x and y. So we can take this, which is like our starter solution, and put it down here. And notice that's going to give us xk equals 3 times xk minus 1 plus 8 times yk minus 1. So we have that nice recursion for xk, and then we have a similar one, yk equals yk minus 1, and that is times 3 plus xk minus 1. Okay, good. So these are our recursions that will define these solutions xk and yk. Okay, so I'll move that to the top, and then we'll keep going. Okay, so far we've built up to the following fact. So all solutions to m squared minus 8n squared equals 1 are in this sequence of ordered pairs xk, yk, where I should say here x1, y1 equals 3, 1. And we have this nice recursion. So xk plus 1 is 3xk plus 8yk, and yk plus 1 is xk plus 3yk. Okay, good. So now notice I've re-indexed these a little bit, but that's just because it's kind of helpful for exactly what we're doing. Now the next thing I want to do is look at these one step lower. So notice this is equivalent to xk equals 3xk minus 1 plus 8yk minus 1, and yk equals xk minus 1 plus 3yk minus 1. So now what I want to do is I want to take this second equation and multiply it by 3 and then subtract it from the first equation. And let's see the motivation here. So let's recall that our y part of this ordered pair gives us our balancing number, which is really our goal. And so what we want to do is somehow combine these in a certain kind of way so that we have a recursion for the y terms only in terms of the y terms and not involving the x's as well. So notice that's going to cancel out this x part. So notice here we're going to have xk minus 3yk. That's what we get on the left-hand side of the equation. Now we'll have 3xk minus 1 minus 3xk minus 1. And then we'll have 8yk minus 1 minus 9yk minus 1. So that's going to give us minus yk minus 1. Okay, great. But now, notice we can rearrange this a little bit, and that allows us to write xk equals 3yk minus yk minus 1. Now the next thing we want to do is take this value for xk and insert it into this recursion right here. So let's see what we get when we do that. So we have yk plus 1 equals 3yk minus yk minus 1, and then plus 3yk. So in other words, we have 6yk minus yk minus 1. And then recall that the y parts were giving us our balancing numbers, so we have this two-step recursion for the balancing numbers. So I'm going to clean up the board, then I'll bring this to the top, I'll rename these as balancing numbers, and then we'll move on from there. Okay, so let's see where we are. I've renamed our balancing numbers from YKs to BKs because now we're really back in the balancing number world and we are not worrying so much about that quadratic Diophantine equation that we got. So the kth balancing number BK is given by the following recursion. So BK equals 6 times the previous one, BK minus 1, minus BK minus 2. And then let's recall we have our two seeds, B1 equals 1 and B2 equals 6, which we got from playing around with that earlier. So now what I want to do is find a closed formula for these, and we'll do that via generating functions. So let's go ahead and set capital B of x equal to the sum k equals 1 to infinity of bk times x to the k. And I have a video where we find the generating function for the Fibonacci numbers previously, and we'll use the same kind of strategy here. So I want to take out the first two terms here. So notice the first term is going to be 1 times x to the 1. In other words, we'll have x. And then the second term will be 6x squared, and so that's because b1 is 1 and b2 is 6, and then that's attached to the correct power of x. And now we'll have this is plus the sum k equals 3 to infinity of bk x to the k. Now the next thing we want to do is apply the recursion to all of those leftover terms. So that's going to give us x plus 6x squared plus the sum k equals 3 to infinity of bk minus 1 times 6 minus bk minus 2 times x to the k. Okay, so now I'll go ahead and split that sum into two parts. So we have x plus 6x squared plus 6 times the sum k equals 3 to infinity of bk minus 1 times x to the k. Good. And then minus the sum k equals 3 to infinity of bk minus 2 times x to the k. Okay, so now I'll go ahead and bring this up and then we'll keep going. Okay, so I've brought my previous step to the top, and I've also factored some x's and x squareds out. So we have b of x, which is our generating function for these balancing numbers, is given by x plus x squared plus 6x times this sum, k equals 3 to infinity of bk minus 1, x to the k minus 1, and then minus x squared times the sum k equals 3 to infinity of bk minus 2, x to the k minus 2. So now we want to re-index these sums so that we can write them back in terms of the original generating function. So here we will replace k with k plus 1, and here we'll replace k with k plus 2. So let's see what that does for us. So we have these terms just to bring down. So x plus 6x squared plus 6x times the sum k equals 2 to infinity of bk x to the k. Okay, so that's what we get for that one. So notice we had to change our starting point from 3 to 2. And now we have minus x squared times the sum k equals 1 to infinity of bk x to the k. So now notice that this guy is already equal to b of x, which was our generating function. But this guy is missing one term. So notice it's missing the very, very first term. So we can go ahead and add that very first term in and then subtract it out. So that's what we'll do. So we'll take this guy right here. So we'll add the first term in by changing that sum so that it starts at k equals 1 to infinity of bk x to the k. But then we have to subtract that out as well, and we'll do that by adding a negative x. Okay, good. And now notice that's all multiplied by 6x. So now let's see if we bring this down, what do we have? We have x plus 6x squared plus 6x times the quantity negative x plus b of x. Great, because now this is the right generating function. And then minus x squared times b of x. Okay, good. But now notice we have x minus times negative x, so that's going to give us negative 6x squared. So in fact, this is going to cancel with what we get when we distribute that. Okay, great. So what we have in the end is we will have x, and then plus 6x times bx, minus x squared times b of x. So that's what we end up with. Okay, so I'll bring that to the top and then we'll keep going. Okay, so on the previous board we left off at this point, so we've got this functional equation for our generating function for our balancing numbers. So now notice we can move all of the terms with b of x over to the left-hand side of the equation. So that'll give us b of x minus 6x b of x plus x squared b of x equals x. So that's all that's left on the right-hand side of the equation. Now we can factor a b of x out of this. So notice if we factor a b of x out of this, we're going to have x squared minus 6x plus 1. Great, and now that's so that's going to be equal to x, b of x times this polynomial, which tells us that b of x equals x over x squared minus 6x plus 1. Okay, great. So now I'll go ahead and move that to the top, and then we're almost ready to get closed form for these numbers. Okay, so we ended at this. We have the generating function for the balancing numbers is given by x over x squared minus 6x plus 1. And now I'm going to do something without showing all the details. I'm going to notice that this thing factors, and you can figure out how it factors by solving x squared minus 6x plus 1 equals 0 with the quadratic formula. And this guy is going to factor in the following way. It'll factor x minus 3 plus 2 root 2 times x minus 3 minus 2 root 2. Great. So now let's maybe write that in the following form. So let's maybe say alpha equals 3 plus 2 root 2, and let's say beta equals 3 minus 2 root 2. And so we can write that in a more succinct form as x over x minus alpha times x minus beta. Now the next thing we want to do is decompose this with partial fraction decomposition. So in other words, we want to write this as a over x minus alpha plus b over x minus beta. So now we'll do that by multiplying both sides of this equation by the denominator. And notice if we multiply both sides of this equation by the denominator, the left-hand side will give us x. And then the right-hand side, keeping in mind that this denominator is x minus alpha times x minus beta, we will get a times x minus beta plus b times x minus alpha. Good. But now notice we can combine like terms over here. We get a plus b times x. Good. And then minus a times beta plus b times alpha. Okay, so now equating the coefficients of x on both sides of the equation and the constants on both sides of the equation, we get the following. So the coefficients of x on both sides of the equation will give us a plus b equals 1. And then the constants on both sides of the equation will give us a times beta plus b times alpha equals 0. So now notice we have a system of equations with 2 equations and 2 unknowns. So notice our 2 unknowns are a and b, and these are our 2 equations. So I'm going to go ahead and write this as b equals 1 minus a, and now we can put that into this equation. And so notice that's going to give us a times beta plus 1 minus a times alpha equals 0, which is going to give us a times beta minus alpha plus alpha equals 0. But now notice that beta minus alpha is a nice number. So beta minus alpha is going to give us 3 minus 3, and we'll have negative 4 root 2. So this is negative 4 root 2 times a equals negative alpha, which tells us that a equals alpha over 4 times the square root of 2. Okay, so now we know what a is. I'm going to clean up the board and we can use that to calculate b. Okay, so on a previous board, we calculated that A was equal to alpha over 4 root 2, where alpha is this number, and now we have B as 1 minus A, so that is going to be equal to, let's write this as 4 root 2 over 4 root 2 minus alpha, but alpha is equal to 3 plus 2 root 2 over 4 root 2. Okay, so let's see what we get when we do that. We're going to have minus 3 in the numerator. Now we have 4 root 2 minus 2 root 2, so that's going to be plus 2 root 2 over 4 root 2. Now we can pull a minus sign out of that and notice that that will be minus beta over 4 root 2. So this is what we have for B. Okay, so we have our partial fraction decomposition for A and B. Good, so I'll clean up the board and then we will move on from there. Okay, so our partial fractions brought us here. So we have b of x is equal to 1 over 4 times the square root of 2 times the quantity alpha over x minus alpha minus a beta over x minus beta. So now I'm going to rearrange this a little bit. I'm going to write this as 1 over 4 times the square root of 2. I'm going to take this minus sign and absorb it into the denominator to write this as beta over beta minus x. Good. And then I'm going to pull a minus sign out of that to do something similar. So this is minus alpha over alpha minus x. And I'm doing this because I want to expand these as geometric series eventually. So now the next thing I want to do is factor a beta out of this term in the denominator and an alpha out of the other term in the denominator. And I can cancel those in the numerator. So that's going to give me 1 over 4 root 2 here, and then I'll have 1 over 1 minus x over beta. So I've got that, and then minus 1 over 1 minus x over alpha. And now I can use a geometric series formula to rewrite this as 1 over 4 times the square root of 2. And then this is going to be equal to the sum, k equals 0 to infinity, of x to the k over beta to the k minus x to the k over alpha to the k. So, but notice that we don't need the k equals 0 term here because that will cancel, and that will give us exactly equal to 1 over 4 times the square root of 2 times the sum k equals 1 to infinity of, we can write this as 1 over beta to the k minus 1 over alpha to the k times x to the k. So, next thing I want to do is I'll take this to the top, and then we're almost ready to write down a closed formula. Okay, so on the previous board we had the following. So the generating function for the kth balancing number was given by this 1 over 4 times the square root of 2 times the sum from k equals 1 to infinity of 1 over beta to the k minus 1 over alpha to the k times x to the k. So now I want to combine those together, so I'll give myself a common denominator, which is beta k alpha k, and that will give us the following. So this is 1 over 4 root 2 times k equals 1 to infinity of, so that's going to give me alpha to the k minus beta to the k over alpha beta to the k times x to the k. So that's just finding a common denominator there. But now let's notice that alpha times beta is actually a nice form here, and that's because these are radical conjugates of each other. So this is going to be 3 plus 2 root 2 times 3 minus 2 root 2. So that's going to give me 9 minus 2 root 2 squared, which is 8, which is 1. So notice all of that cancels. So that means alpha times beta is 1, which means alpha times beta to the k is also 1. So in other words, we get this is 1 over 4 root 2 times the sum k equals 1 to infinity of alpha k minus beta to the k times x to the k. But now extracting coefficients, what we have is that bk, in other words, the kth balancing number, is given by 1 over 4 times the square root of 2 times alpha to the k, but I'll rewrite what alpha is. So this is 3 plus 2 root 2 to the k minus beta k, so that's 3 minus 2 root 2 to the k. So now we have a nice closed form for the kth balancing number. So I'm going to clean up the board and then we'll look at a summary of everything that we've seen. Okay, so after all of that, we have this nice summary. So the kth balancing number is described these nice 3 different ways. So we have this 2-step recursion, so bk equals 6bk minus 1 minus bk minus 2, where b1 is 1 and b2 is 6. We have this nice closed formula, so bk is 1 over 4 times the square root of 2 times 3 plus 2 root 2 to the k minus 3 minus 2 root 2 to the k. And also it's given by this generating function. So the sum from k equals 1 to infinity of bk x to the k is x over the quantity x squared minus 6x plus 1. So we've done a lot in this video and I think this is a good place to stop.